So first, let's take a look at the unilateral gain method. So starting with the expression for the unilateral transducer gain, we can rewrite it. We can rewrite the expression at the top in terms of these three parameters, which represent gains associated with the input matching network, the output matching network, and the transducer itself. So again, this is under the assumption that the parameter S12 is equal to 0, or very small. So the idea here is that we have the S parameters for the transistor. So this gain here, the G0, it's in terms of S21. That's sort of an intrinsic gain of the transistor itself. So what we end up doing here is we end up adjusting the input and output matching networks in order to achieve the desired gain. Okay, so let's start with the input matching network here. We know that if we match the impedance seen looking into the input matching network with the impedance seen looking into the input of the transistor here, then we will achieve a perfect match, which will result in maximum power transfer into the transistor. So in terms of reflection coefficients, the input reflection coefficient is normally written like this, we talked about last time. It's in terms of the matching network at the load. But in this case, we're making the simplification that S12 equals 0. Okay, so our input reflection coefficient reduces to just S11. It's one of these situations here. So if we match the source reflection coefficient to the complex conjugate of S11 and we plug that into this equation up here at the top, then we end up with the maximum gain associated with the input matching network like this. So we can use this to normalize GS to GS max, resulting in this equation down here. So from this equation with the normalized little g sub s here, after some algebraic manipulation, you can arrive at our first gain circle corresponding to the input matching network. So again, the center of the gain circle is given by this parameter here, and the radius of the gain circle is given by this parameter here. So to see an example of this being used, let's consider example 9-7. So we have a FET operating at 4 gigahertz, and it's biased such that S11 is 0.7 with an angle of 125 degrees. We assume that the transistor is unconditionally stable, and it asks us to use a unilateral approximation. And they are asking for the constant source gain circles for several values of gain here. So it's very simple. So we plug in the value for the magnitude for S11. We end up with our value of G sub S max. In terms of dB, it's 2.92. So now turning our attention to this table up here, starting from the bottom, we can plot a circle corresponding to 41% of this maximum gain. So basically, we would plug in 0.41 for GS in both of these expressions. We would plug in our expression for S11, which is given up here in the problem, in both of these expressions. And we would end up with a circle that's centered at this location and has a radius of this. This would correspond to a gain of -1, so that is the circle that you see here. Next, we can plot another constant source gain circle for 51% of this maximum gain. Again, we plug in 0.51 for GS, and we plug in our value for S11 that's given in the problem, and we end up with another circle that has a center at this location and a radius of this. So this corresponds to a gain of 0 dB, which is this circle here. So we can continue to look at all of the other values that are in the table here. One thing I want to do is I want to point out that this is in the gamma S plane. Okay, so you can see here the circle equation is in terms of gamma S. And that makes sense because if we go back to this expression here, we are concerned about GS, and that is the source, or sorry, the input matching network on the source side here, G sub S. Okay, so all of these circles are in the gamma S plane. That's a very important concept. All of these points on these circles here, so let's just take the -1 dB circle here for a second. So what this means is if we want G sub S, the input matching network, to have a gain of -1 dB, then that means that the impedance seen looking in to the source, the input matching network, has to be one of the impedances that reside on this circle. Okay, so you can see that with this lower value for gain, we have a huge number of impedances that we can choose from. But let's take a look at this point here. Okay, we already said that in our derivation of this expression for GS max, This occurs when gamma S is complex conjugate matched to the S11 parameter of the transistor. So if gamma S equals S11, the complex conjugate of S11, that would just be 1 point on the gamma S plane here, and that would correspond to our maximum gain of G sub S. Okay, so if we did that, if we matched the input of the transistor to the input matching network, and we ended up with a gain of 2.92 dB in this example, and let's say that G naught, which was S21 squared, if we convert that to dB and we plug in the value for this transistor, let's just say that it's 10 dB, then the total gain due to the input matching network and the transistor itself would be 12.92 dB. Okay, so we took this example a little bit further. I just wanted to hopefully make that perfectly clear. So with the input matching network and the transistor, we might have a gain of 12.92 dB, let's say. But what about the output matching network? So there'd be a gain associated with that output matching network as well. Okay, and that gain would be given by this expression here. So basically you can come up with another gain circle for the output matching network here, in this case, for the unilateral transducer gain. Basically we can follow the same format as last time. We can perfectly match the load to the output of the transistor. We can come up with the GL max, normalize that, come up with this G sub L, and then from there you can come up with a whole other set of gain circle equations for the output matching network here. Okay, and it would be exactly the same as last time, the implementation of it. Just make sure that in order to use the unilateral gain method, S12 has to be very small. So next, we can use the expression that we have for the transducer gain in terms of gamma in, and we can use this expression to derive an equation for what is known as the operating gain. Okay, so for the first one, we looked at the unilateral transistor gain, and this makes the assumption that S12 equals to 0. For operating power gain, this makes the assumption that the input to the transistor is perfectly matched to the input matching network. Okay, next class we'll see that the available power gain is going to make the assumption that the output is perfectly matched to the load. Okay, so just keep these three approaches in mind here, and we'll move on and discuss the operating gain. So we can start with the expression from the previous slide, and we can plug in our expression for gamma in like this, make some simplification, and basically end up with another set of gain circles, okay, where we have this time circles that are plotted in the gamma L plane. That's very important to point out. Make sure that you're aware of this, that so far for the unilateral gain method, we can have circles in the gamma S plane when we're talking about the input matching network, and we can have circles in the gamma L plane when we're talking about the output matching network. Here, so far, with the operating power gain, we have gain circles that are only in the gamma L plane so far. In the next lecture, we're going to see how to map these circles from the gamma L plane to the gamma S plane to be used with noise circles.